Hello class, we're ready for sections 1.3 and 1.4. We're going to cover those both in one video, so make sure you read both those sections before watching this for college algebra. All right, so the topics today are going to be talking about relationships and then talking about functions specifically and some of the language we use with those functions. So you'll know what all those words mean by the end of this video, okay? So the first thing I want to talk about is just relationships in general. So in section 1.2, we started talking about how do we look at two variables together. We visualized that relationship between two variables using scatter plots. So what we're going to do now is take those two variables and talk about, okay, what are some other things we want to look at with that relationship? So we can describe those relationships as we did in section 1.2 with those ordered pairs looking at scatter plots. We can describe relationships between two variables using ordered pairs and thinking about x and y too in a couple of different ways. So x can be thought of as our input variable and y can be thought of as our output variable. So we don't always have to think about those in terms of x and y. We can think about x as input and y as output. Or if you've heard, right, of independent and dependent variables, x is always your independent variable and y is always your dependent variable. So those things go hand in hand. So just talking about that last time and kind of looking at that here. Now, a few new ways that we're going to look at in these sections to talk about relationships are using words, equations, tables, and graphs. So we can summarize those relationships in these new 4 ways. So I'm just going to kind of give you an example of how we would talk about a relationship in words. So here's a relationship between two variables described in words. Here's our example. We're going to say the sales tax is 6% of the purchase price. And in that one sentence, I have described the relationship between two variables. Can you identify what those two variables are? The two variables would be the sales tax, how much am I going to pay in sales tax, and the other variable is the purchase price. Now, in words, we would then have to think through, okay, I have my two variables, but which one would be the input and which one would be the output? In this case, which thing affects the other thing? If I want to calculate my sales tax, I need to know how much I'm buying, my purchase price, before I know how much I'm going to pay in tax, right? Think about going to the store in the order of those things, right? You choose what you're going to purchase, that has a price, then you go to the cash register and you pay for it and you pay for sales tax at that point. So in this case, our purchase price would be our input variable and our sales tax would be our output variable. And it's always that's kind of the hardest part at the beginning here when you don't have those described in terms of ordered pairs, right? Because when you have the variables in ordered pairs or in a scatter plot, that decision is made for you. But using words, you have to kind of think through and do some problem solving, some critical thinking with that, and decide what would be our input and what would be our output in this case. In section 1.2, we talked about how using equations is very powerful for describing relationships. So what we're going to do is now come up with those equations. So we're going to take this same relationship that we just represented in words, and we're now going to represent it using an equation. Now, equations typically use those x and y variables, but you can use any letters you want for the variables. The first thing you're going to do when using an equation is make sure you set up your variables. We know one of our variables using words is sales tax and one variable is purchase price. So make sure that you put the right letter to those variables. If you come up with your own letter, then you don't have to worry necessarily about x versus y. I'm going to come up with my own letter just so I can keep track of what these variables mean. So I'm going to say that P is going to represent my purchase price, so I can remember that easily with the P. And I'm going to use the variable T to represent how much sales tax I pay. Okay, I kind of like to curl my T's so they don't look like plus signs. So this is also a hard step, right? What would be the equation that describes how much sales tax I'm going to pay given a purchase price. So this is where we're going to take this 6% into account up here to come up with the equation. Now, one thing to look at that makes this a little bit easier is that typically our output variable will be by itself. So I'm going to try and solve for my sales tax. So that should be in terms of the purchase price somehow. So on the right-hand side of this equation, I'm going to have my purchase price. But how would I calculate the sales tax knowing the purchase price and knowing that my sales tax is 6% of the purchase price? And I can kind of do that by looking through these words. So sales tax, there's my variable for sales tax, typically is an equal sign. And then I see this 6%. We're always going to represent percentages by decimals when we're doing math with them. So I would have 0.06. Typically when I see this word of, it means to multiply. And that's exactly what we're going to do because I want to find 6% of the purchase price. When I'm finding a percentage of something, I'm going to multiply it times that thing. And the purchase price is P, so I need to find 6% of P, which means I need to take 6% times P. So that's how I would calculate my sales tax each time. And now I have this awesome equation that no matter what my purchase price is, I can just plug that in and get my sales tax. I have an equation now to represent this relationship. We can also describe relationships by looking at several values that are true for that relationship and summarizing those values in a table. Now, using a table, we'll have two variables set up, and typically our input will always go on the top if we have a top and a bottom, if we have two rows for our table. Our input variable here is P, and our output is T. So again, typically if you have a table, your input will go in the top, and your output will go in the bottom. Sometimes you have tables vertically, in which case you have your input on the left and your output on the right of that table. And you would have a table kind of set up like that. All right, so just kind of traditional ways to set up tables. Now, what we want to fill in here for the rest of the table is our values that are true for this relationship. Since we have an equation, we can come up with some of those values. So I'm going to pick some values. Remember, finding solutions to equations. I'm going to pick some values for P and then solve for T in order to get a table of values. So you can pick any value for P that makes sense. Here, a negative value would not make sense because we wouldn't buy something for a negative amount. But we could start with something as simple as 0. You could purchase $0 worth of things, and how much sales tax would you pay? Well, you plug in 0 for P here, and you see that your tax would be 0, right? You wouldn't pay any tax if you had nothing to buy. And then we can just go up simply here. Maybe I'll plug in $1, then $2, then $3, and $4 for my purchase price and calculate the different tax amounts. So if I take 0.6 times 1, I'll pay 6 cents in sales tax. If I take that times 2, my output will be 0.12 or 12 cents in sales tax. Then I'll get 0.18 when I plug in 3 for P here. And if I plug in 4, I'll get 0.24. So I can use all these different ways to represent relationships to help me come up with the consecutive ways to look at relationships here. So I've got words, I've got an equation, I've got a table, and then the graph is the one that we've kind of already looked at, right? We've looked at those scatter plots, and that's what we're going to create here. So let's use our table of values. We have a bunch of different coordinate points here that we know are true, and let's put those coordinate points on the graph to describe this relationship. Now, which variable would go on my x-axis down here? Would I be putting P on that axis or my coordinates T? And hopefully there you said P, right? Your input variable always goes on the x-axis and your output variable always goes on the y-axis. And that's why I have the scale set up like I do. So if you'll notice here, we're going by whole numbers. I'm going to throw in those extra whole numbers there to make sure I understand my scale. And I'm going to have to plot things like 0.06 and 0.12 on my y-axis or my t-axis in this case. So let's see what our scale is going by here. Notice I have 1, 2, 3, 4, 5 steps to get to 0.1. So if I divide 0.1 by 5, I'll get 0.02. So I'll know that each one of these steps is worth 0.02. So I can kind of label those to help me graph this here. Kind of getting that pattern down. Okay, if you weren't given a graph, then you would set up that scale yourself. So now can you plot each one of these 5 points? So notice this right here, 0, 0 is a point, then 1.06 is a point, and so on. So if we plot each one of those points, 0, 0 is down here, then 1.6 would be right here, 2.12 would be up here, 3.18 would be up here, and 4.24 would be right here. And when we're doing a graph, we can connect those to see that overall graph that's happening. And we see now how the relationship between P and T is visualized using that graph. We use a table of values to get to that graph as well. So mostly 4 or 5 different ways we can look at summarizing relationships: graphs, tables, equations, words, and a set of ordered pairs. Okay? Now, with those relationships, we're very interested in relationships that follow the rule for what's called a function. So we first need to know what is a function. How would a relationship be a function? So a relationship is a function if it is a rule that assigns each input quantity to exactly one output quantity. And we're going to talk about exactly what that means here in a second. But every input goes to exactly one output. And if that is true, we say then that the output is a function of the input. And this will be very important here that you remember this order. It's very important that we say it exactly that way because we don't want to switch those two around. It would be a different thing to say, if we say y then is a function of x because y is the output and x is the input, that is not the same thing as saying x is a function of y. That's an entirely different statement. So very important to remember these two things. The order of how you say that is very important. So let's talk about this. What does it mean for an input to be assigned to exactly one output? So we're going to look at some relationships and decide if they're functions. Let's start by looking at some relationships in tables and decide if these are functions. So if I look at this first relationship here in part A, does each input have exactly one output? So I see an input of 1 here, and it has exactly one output of 6. I see an input of 2, it has exactly one place to go, 7. If I input 3 into this relationship, I know exactly what my output will be. It'll be 8. And same thing with my last input of 4, it will only go to 9. So what we're thinking here is that if I plug something into this function, I know exactly what my answer will be. There's no question about it. So this is a function. So yes, this is a function. Each input goes to exactly one output. Now, what about this next one here? Does this relationship describe a function? You see a problem, hopefully here in the first 2 entries. If I plug in 1, I could have to go to 6, or I could have to go to 7. I don't know where to go for this function. If I plug in 2, I'm okay, and if I plug in 3, I'm okay. But if there's any one input that goes to more than one output, we have a problem. We don't know where to go when we plug in 1, and this is not a function. So hopefully that definition is starting to make more sense as we look at those tables. So now, in this next one, can you tell me, we've got 2 variables here, Y, year, and U, the unemployment rate in the US in that year. Can you tell me if u is a function of y? Now, remember how important that order was? So this means that u is going to be our output, and this means that y is going to be our input. So the table is set up like we would anticipate. Here we have the input, and here we have the output. So for every input for every year, do I know exactly what the unemployment rate is? Yes, each year goes to exactly one unemployment rate, which makes sense, right? Every year should only have one unemployment rate that occurred that year. So this is, yes, u is a function of y. Every year has exactly one unemployment rate. We satisfy that definition of a function. Okay, but what about switching those two things around? That changes the question entirely, right? So for this next one now, we're talking about, is y a function of u? So now we've switched this around. Y is going to be our input, and u is going to be our output. So our table won't be set up typically. So write that down for yourself. Now over here, you're thinking about this is the input and this is the output. So you're going this way with the table. And you're asking yourself then, if I pick an unemployment rate, do I know exactly what year that occurred in? So as you go down the table, it works for 8.5. 8.5 does not get repeated for the rest of the table. If you have an unemployment rate of 8.5, you know that happened in 1975, at least for this set of data. But can you find any unemployment rates where if you were to pick that unemployment rate, you wouldn't necessarily know what year that occurred in? And we do have a problem here with the unemployment rate of 5.6. That could have occurred in 1990 or in 1995. So that means that there's no way that y is a function of u. And I'm sorry, I just wrote that down incorrectly. This is our output, and this is our input. I wrote it down over here correctly. I just realized that the first time I wrote that down, I switched those two around. Okay, we've done the whole problem correctly. I just realized that was a typo there. Okay, so because that input of unemployment rate, we don't know necessarily what year the output that occurred in, this is not a function. Okay, so no, 5.6 occurs in two different years. Okay, so hopefully that makes sense there. All right, let's talk about what this means now in a graph. We understand what it means for a relationship represented by a table, and we now understand what it means, how important it is that we understand that order and make sure we understand that order, which one's output and which one's input. So determining if it's a function or not from a graph. Excuse me. The nice part about a graph is we have a visualization, and there's really an easy way to determine with the visualization if it's a function or not. And that's by employing the vertical line test. So if there is a vertical line that intersects the graph of a function more than once, then the graph does not represent a function, and you failed the vertical line test. So I want to talk about what this means. Here I've got the graph, a relationship between two variables. My vertical line test says that there's any vertical line, I'm going to draw an example of a vertical line here, that intersects the graph more than once, we don't have a function. Notice this vertical line intersects the graph only once. As I continue to think about other vertical lines, so I'm just drawing examples here, but if there's any vertical line that would intersect this graph more than once, we would have a problem. But in this particular case, there's no vertical line I can think of here that would intersect the graph more than once. So that means every input, every x value has exactly one y value. We've passed the vertical line test, and this is representing a function. So yes, this passes the vertical line test. So this is a function. And it's as simple as that when we have a graph. So just to make sure we're understanding this, this would not represent a function, because if I draw a vertical line right here and all I need to find is 1, it passes through twice. So that means my input, if I pick an x value of 5, I don't know whether or not to go to this output or this output. So I failed the vertical line test. This fails the vertical line test. So this is not a function. There's an input that has more than one output. And that vertical line tells us that right away. And these are actually the only two ways that we'll look at relationships and determine if they're functions. The graph is the best way, right? It's the quickest way and easiest way to tell. And we can always graph equations. So if we're ever given the equation, we would create the graph to tell if it's a function and go from there. And then if we're given a table of values, we can tell pretty easily as well. Okay, so we'd always change our relationship if we had it represented in another way to one of these two ways, either a full table of values or a graph, in order to tell if it was a function or not. So hopefully that function definition is making more sense. All right, now, once we know if something is a function, then what we'll do is we'll write our equation in a special way to tell us, hey, this equation right here, you don't need to graph it or do anything with it to tell if it's a function. I'm telling you by writing it this way that it is a function. And that notation is that instead of using y for our output variable, we're going to use what's called function notation, which is read f of x equals y. So this over here is not multiplication. This is our function notation read f of x, kind of like thinking this is a function of x. Okay, now it's a little bit wonky and we tend to want to think that that is multiplication going on, but it's not. So what I want to do is look at how to use function notation in equations and tables and things like that so we can get used to this notation and what's being asked of us when we see this notation. So let's start with equations. So this is an equation right here written in function notation, and it tells me immediately that 3x plus 2 is a function. So if I were to graph this relationship, it would pass the vertical line test and it's a function. So what does it mean when I say find f of 5 for this function? So when you see this, what you see is that x has been replaced with a 5. So what we need to do is do the same thing in this equation. F of 5 then means that I need my x in my equation to be a 5, and then I just need to solve. So f of 5 equals 3 times 5, which is 15, plus 2, which equals 17. So f of 5 equals 17. So when you see this notation, you're being asked to find an output value. What you're also seeing here is that if you plug in 5, you get out 17. So we've found a coordinate point that is true for this relationship. Can you figure out then what g of negative 2 is if our function is g of x equals x squared plus 1? So notice here, just like y can change letters, the f can change letters. The x could also change letters, but this is still in function notation. Anytime we see one letter with another letter in parentheses. So can we get this output value? G of negative 2. Make sure anytime you have a negative number, you plug it in parentheses. So negative 2 needs to be squared, and then we need to add 1. Negative 2 squared in parentheses is a positive 4, and 4 plus 1 is 5. So our answer is 5, And what this means as we're thinking about it is that if I plug in -2, I get an output value of 5. We sometimes have more than one place to plug in an input value. That's all right. So here, if I'm finding h of 7, that means I need to take 7 for the x in the top and 7 for the x in the bottom, and just simplify. That means I get 7/10, which is a simplified fraction, and I'm done. It means that if I plug in 7 for my input variable, I'll get 7/10 out for my output variable. So this notation is giving you an input and asking for an output. The way you'd see it if you were given an output and asked for an input is like this down here. So here again, I'm given my function notation, but this time I'm told my output is 2, and I want to find when that happens. So I'm being asked for the x value, or whatever the input letter is. So f of x is 2, so that means I have 2 for my f of x, and I have nothing to put in for x here, so I need to solve for x. That's just going to require a little bit of algebra. We need to add 2.5 to both sides in order to start getting that x value alone. That leaves us with 4.5 equals 5x. That means I need to divide both sides by 5 to solve for x, and that tells me that x is 0.9. So I found when my output variable was 2, so I was being asked to find the input given the output. So that's how it would look differently when you switch around what you're given, input versus output, in this function notation. All right, we can also find these input and output variables given a table. So let's look at what function notation in tables looks like. So here's our table. We have our input on top and our output on the bottom. Our output is now in that function notation. So here again, we just have a list of ordered pairs that satisfy the function s of x. So can you find for me what s of 0 is? That means you're given an input and you're looking for the output. You're given the input is 0 and you're looking for the output. So if my input is 0, my output is 0. Can you do the next one? Here, you're given an input of -1 and you're asked for the output. My input is -1, then my output is 1. We do need to be a little bit careful sometimes when we switch this around. So if I find x when my output is 4, now inputs cannot be repeated for a function, but outputs can be. There's nothing saying that an input can't go to the same output. Each input just needs to go to exactly one output. So here I have to be a little careful. I have 2 values for when s of x is 4. So I need to report 2 input values where this occurs. It occurs at both x equals -2 and x equals 2. So I'd say x equals -2 and x equals 2. I get 2 answers here when I'm looking for my input values. If you're ever looking for an output value though, you know it's a function, so you'll always only have one answer. All right, let's do our last way we would work with function notation, which would be with graphs. So here I have a function f of x being represented by this graph right here. I want to find f of 0. That means I know x is 0 and I'm looking for my y. I want to know what y equals. So if x is 0, that means I'm on this line here, right? This is the only place x is 0. And if x is 0, it must be that y is 5. There's my point on my graph where x is 0. So my answer here would be that y equals 5, and that's my output when my input is 0. Here again, this means I'm given an input and I'm being asked for my output. So can you tell me if your input is -4, what your output is? X equals -4 is right here, and I'm already on the graph. So that means my output is 0 when my input is -4. What about this next one? Always look for multiple values too when you're given the output but being asked for the input. If my output is 8, what is my input? Where is your output 8? Your output is 8 right up here. So if my output is 8, I'm looking along this horizontal line now to say, okay, these are all my values. Where my output would be 8. Where am I crossing my graph? Oh, at an input of 9. So my only answer here would be x equals 9. There's only one output where my input, there's only one output equal to 8 and my input must be 9. Okay, so always just remember what you're being asked when you see these notations. If x is replaced, you're given the input and looking for the output. If x is not replaced, you're being given the output and you're looking for the input. Now might be a good time to pause, take a little break. We're going to switch gears and talk about the last topic, which is domain and range. So the first thing is that we need to understand what is domain and what is range. So domain focuses on input values, where range focuses on output values. And we want to talk about all possible input values and then all possible output values. So we're going to find domain and range given graphs or given some context of our variables. So let's start with graphs because that's the easier way to think about domain and range and kind of an easier way to understand what it is right off the bat. So here's a function, it's being graphed here. We can see by these points right here that the graph stops at these points and does not continue on. There are not arrows at the end of that graph. That's important when thinking about where our possible input and output values are. Now here, remember, for domain, we're thinking about input values. That means we're thinking about our x-axis. So I want to think about where does my graph live along my x-axis? Between what values? So my graph lives between an x value of -5 all the way to an x value right here. See if I can follow along that line there, to an x value of 13. Now, we will report our intervals in interval notation. That is not something we review in this class. It's something I'm assuming you're coming in with the knowledge of. But if you're not sure about that, I've posted the interval notation handout in Talon. Make sure you pull that up and look at it to understand where these interval notations are coming from. So all my x's, I can find any x, any input value, anywhere in between -5 and 13. Now, I see there, so again, I'm gonna drop that down, so that's 13 right there. Those values are included since I see these closed circles right here. So I'm gonna show the interval between -5 and 13. So my interval goes as low as -5, as high as 13, and for interval notation, we will use brackets to show that those 2 points are included. I could plug in a -5 and get an output. I could plug in a 13 and get an output. So I want brackets to show that those inputs are included. All right, now for range, we do our y-axis. So for range, I'm focusing on my y-axis and thinking about how low does this graph go and how high does this graph go. Now the lowest this graph goes is it hits a value down here at -5, and there's graph to be filled in all the way up to 15. So my range includes -5 and goes all the way up to 15. So that would be my interval where I can have any y value, right? In fact, in some cases, and that's okay, I have multiple y values anywhere in between those 2 values and nothing outside of those 2 values. So that is my range. Range is always your output or y values. Okay, so give this one a shot. This one's going to look a little bit different though, because here I don't have those clear endpoints, so I assume this graph goes on forever. So as you start to think about domain and your x values, is there any x value you cannot get to? And there's not, because this graph goes forever to the left and it goes forever to the right. It grows forever left and right. So there's all the numbers. I can get to every number. So I would say either I can go all the way to the left and all the way to the right. Those are negative infinity and positive infinity signs. Or the other way you can say this one is that you can get to any number. So we would say all real numbers. Okay, either way of saying that is okay. If you do it in interval notation, though, this is interval notation. What about the range? How low and how high does this graph go? Again, if you assume it goes on forever, it goes down forever and it goes up forever and fills in all the values in between. So your range would be negative infinity to infinity as well, or all real numbers. Okay, so again, if you're not recognizing that interval notation, just go look at the handout that I had posted, and that should remind you of what interval notation is. Let's do one last example with domain and range when we're talking about it in context. So we can often tell what values make sense for a variable, for an input or output variable, given the context of that variable. So right here, we want to find the domain and range of c equal to 2.72 times g. Now at this point, it's a little bit harder to find domain. We'd probably have to graph the function or something like that to figure that out. But as soon as we're given context, this will help us. We know G is the number of gallons of gas purchased, and C is the cost in dollars of that gas. As soon as we have that context, we can start to think about what values make sense to plug in. But before we do that, let's start with domain. We have to figure out which variable is domain. So is our input going to be G, or is it going to be C? And hopefully there you answered G, right? Because we plug in G and then we get an output of C in our function. So as I'm thinking about domain, I'm thinking about G. So what values for G make sense? What's a value that makes sense for the number of gallons of gas? Or think about it in the opposite way. What's a value that doesn't make sense? Or what type of values do not make sense? So hopefully here you're recognizing that negative values would not make sense to purchase, right? I can't get a negative number of gallons of gas. I could pay 0 gallons of gas though. And for what we're doing in these purposes, we're gonna assume that gas is unlimited. Now we know that the idea behind that is a little bit crazy, but we don't know what that maximum amount of gallons would be. So we're gonna assume that this goes on forever because we're not being told otherwise. So if I can have any positive value, any G value on forever, then this goes all the way up to infinity. And we always use a parenthesis with infinity because it's not a number we can reach. Okay, so given the context there, I say, oh, actually, even though I could probably, right, even though I definitely can in this equation plug in negative values, because of the context of G, I don't want to include those in my domain. Then we like to think about range next. Sometimes it's helpful to think about these in the other order, but typically you want to do domain and range, because what you plug in will affect what you can get out. So what makes sense for the cost then? And this has about the same reasoning. I'm not going to pay negative amounts of money. I could pay $0 for my 0 gallons of gas. And then again, because I assumed gas could go on forever, I could purchase as much gas as I wanted. That cost can go up forever as well. So we get domain and range based on the context of that problem, based on what those variables were set up to be. All right, so that's section 1.3 and 1.4. Go give that homework a try and come with questions to class or to me via email.